Good day guys and welcome to my YouTube channel. So today we'll be looking at Cameroon GC Advanced Level June 2019 Physics Paper 2 Section 1. Without wasting much of your time, let's dive straight to the questions.
So question 1 says the capacitance C between two parallel metal plates is given by C equals epsilon naught A over D, where epsilon naught, this here supposed to be epsilon naught, where epsilon naught is the permittivity of air, A is the area of overlap of the plate, and D is the plate separation. Question A, show that the equation above is homogeneous. Question B, if the area of overlap of the plates of a capacitor whose plates are separated by 1.25 exponent negative 6 meters is 1.64 exponent negative 24 centimeters squared, what is its capacitance? Okay, now to show that, question 1a, to show that C equals to epsilon naught A over D is homogeneous, we first of all need to understand what is meant by a homogeneous equation. Generally, a homogeneous equation is one in which all the summative terms in the equation have the same base units or dimensions, or one in which the base units or dimensions of the physical quantities on the left hand side of the equation is equal to the base units or dimensions of the physical quantities on the right hand side of the equation. So to show the equation C equals epsilon naught A over D is homogeneous, we simply need to show that the base units of C is equal to the base units of epsilon naught A over D. Now for the left hand side, we have the following deduction. From C equals to charge over voltage, for which in electric fields we have that V is equal to work done over charge. This means that C will be equal to charge divided by work done over charge, which boils down to charge squared divided by work done. Now but we know that charge is equal to current times time, and work done is equal to force times displacement in the direction of the force. So this implies that the base unit of charge will be equal to ampere second, since current is measured in amperes and time is measured in seconds, while the base unit of work done will be equal to the base unit of force times the base unit of displacement, which is kilograms meters per second squared times displacement measured in meters, which means that the base units of work done will be equal to kilogram meters squared per second squared. So this implies that the base units of C will be equal to the base units of charge all that squared divided by base units of work done. So we have ampere second all that squared divided by kilogram meter squared per second squared. Now starting with kilograms, I will have per kilograms per meter squared second to the power 4, because when this minus 2 goes up, times x to the power 2, we have s to the power 4 times ampere squared. So these are the base units of the left hand side. Now for the right hand side, we have the following deduction. Using the mathematical statement of Coulomb's law of electrostatics, we have that F is equal to Q squared divided by 4 pi epsilon 0 r squared. That is a situation where the charges are placed in a vacuum or in air. This implies that epsilon 0 will be equal to Q squared divided by 4 pi r squared times F. So base units of epsilon 0 will be equals to base units of Q all that squared divided by base units of, that is base unit of R, all that squared, times the base unit of F. We are ignoring 4 pi because 4 pi is dimensionless or it has no unit. Now, base units of epsilon 0 will therefore be equal to ampere second all that squared divided by, here I'll represent separation. So we have meters squared times base units of F, which is kilogram meters per second squared. This boils down to per kilogram per meter cube second to the power 4 times ampere squared. Now, the base units of the right hand side would therefore be equal to the base units of epsilon 0, the base units of epsilon 0 times the base units of A divided by the base units of D. So we have base units of epsilon 0, we have kilogram per kilogram meter cube second to the power 4 ampere squared times base units of area, which is meters squared divided by base units of separation, meters. This will give per kilogram. Meters cube times meters squared will give me per meter squared second to the power 4 ampere squared divided by these meters, which further boils down to per kilogram per meter squared second to the power 4 ampere squared. So the base unit of the right hand side will be equal to per kilogram meter squared second to the power 4 ampere squared. This value corresponds to what we got above for the left hand side, that is per kilogram per meter squared seconds to the power 4 ampere squared. So we can therefore conclude that the equation C equals to epsilon naught A over D is homogeneous. Now part B says if the area of overlap of the plates of a capacitor whose plates are separated by 1.25 exponent -6 meters is 1.64 exponent -24 centimeters squared, what is its capacitance? Now from that information we have been given the separation between the plates D to be equals to 1.25 times 10 to the power -6 meters. We have been given the area of overlap A to be equals to 1.64 times 10 to the power -24 centimeters squared. Now the very first thing we need to do is to convert these values of centimeters to meters. So this will be the same as we divide all this value by 10,000. So you will have 1.64 times 10 to the power -28 meters squared. What do we also know? The permittivity of free space is 8.854 times 10 to the power -12 farad per meter. So if we key all these values in this equation, C equals to epsilon naught A over D, we are going to have C to be equals to 8.854 times 10 to the power -12 farad per meters times the area, which is 1.64 times 10 to the power -28 meters squared divided by the separation, which is 1.25 times 10 to the power -6 meters. Now let me use my calculator. You have C will be equals to 1.64 1.16 times 10 to the power negative 13 farad, and this is the capacitance of the capacitor. Okay guys, let's move over to question 2. Now question 2 demands we distinguish between solids and liquids in terms of the following properties. Roman 1, molecular arrangements. Roman 2, intermolecular forces. Now to do so, in terms of molecular arrangement, first of all, we need to understand the different types of solid that exist. We have crystalline solid, and non-crystalline solid, or we call amorphous solid. Now, with regards to molecular arrangement, in crystalline solids we have regular arrangement, while in non-crystalline solids we have irregular arrangement. Okay, now coming to liquids. Liquids generally have irregular arrangement. Okay, now let's move on to the next property. The next property says in terms of intermolecular forces. In solids, generally the intermolecular forces are strong. So here we have strong, while in liquids the intermolecular forces are weak. That said, we are done with question 2. Let's move on to question 3. Question 3 says two protons A and B, each of mass 1.70 times 10 to the power negative 27 kilograms, are separated by a distance of 1.00 times 10 to the power negative 13 meters. A. Draw a diagram showing the forces acting on the protons. B. Calculate the ratio of the electric force to the gravitational force between the protons. Okay, so we have question 3. Start with 3A. Question 3A says, let's draw a diagram showing the forces acting on the protons. So we have our two protons. We have the first proton A, and we have another proton B. These protons are placed at the same distance r apart in space, and the value of r is clearly 1.00 times 10 to the power negative 13 meters. Now, since these protons are particles and particles generally have masses, so there exists a gravitational force between them, and that gravitational force is attractive. So A will be attracted towards B, given by a force Fg, while B as well will be attracted towards A, given by a force Fg. These two forces, we have they are called the gravitational force of attraction. Now that's not all about the forces acting on A and B. Secondly, A is a proton, B is a proton, and we all know that protons are positively charged. That means between A and B we expect to see a repulsive force. So we have in this direction Fe, and this way Fe as well. These two forces, first of all, they are the electrostatic force of repulsion. That's electrostatic force of repulsion. So the forces are equal in magnitude and opposite in direction, be it the gravitational force or the electric force. They are equal in magnitude and opposite in direction based on Newton's third law. That is, for every action there is an equal but opposite reaction. That said, let's move on to question B. Now question B says calculate the ratio of the electric force to the gravitational force between the protons. To do so, we have from Coulomb's law of electrostatics, the magnitude of the electric force Fe is given by Q1 Q2 divided by 4 pi epsilon 0 r squared, where in this case we assume that the two protons are placed in a vacuum or in air, where epsilon here is the permittivity of free space. So with this, we have epsilon 0 is the permittivity of free space or of a vacuum. Now, according to Newton's law of universal gravitation, we have that the magnitude of the gravitational force Fg between the two protons will be equal to G m1 m2 divided by r squared, where G here represents the constant of universal gravitation. Now, what are the quantities given to us? We have been given the masses of the protons, so we have m of A equals m of B, which is equals to 1.70 times 10 to the power negative 27 kilograms. We have been given the distance r apart between A and B, that is 1.00 times 10 to the power negative 13 meters, and we all know that the charge on a proton is positive 1.6 times 10 to the power negative 19 coulombs. What else do we need? We need the numerical value for the permittivity of free space and the constant of universal gravitation. Now, epsilon 0 is equals to 8.854 times 10 to the power negative 12 farad per meter. Why the value of G is equals to 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. Now, with these parameters, we have that the electric force Fe between A and B will be equal to the product of the charges divided by 4 pi epsilon 0 r squared. So we are going to have 1.6 times 10 to the power negative 19 coulombs, all that squared, because the charge on the two protons are the same. So we have 1.6 times 10 to the power negative 19 coulombs, all that squared, divided by 4 pi epsilon 0 r squared. So we have 4 pi times epsilon 0, 8.854 times 10 to the power negative 12 farad per meters, times the value of r, which is 1.00 times 10 to the power negative 13 meters, all that squared. If you punch this, you're going to have Fe to be equals to, let me quickly punch. Okay, you're going to have Fe to be approximately equals to 2.3 times 10 to the power negative 2 newtons. That is the value of the electric force. What about the gravitational force? So likewise, we have that Fg will be equal to the gravitational constant G times the product of their masses divided by the square of their separation. So we have the value of G is 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared, times the product of the masses, which is 1.70 times 10 to the power negative 27. So we have 1.70 times 10 to the power negative 27 kilograms, all that squared, because the two protons A and B have the same mass, divided by the square of the separation, 1.00 times 10 to the power negative 13 meters, all that squared. If again you use a calculator, you are going to have Fg to be equals to 1.86 times 10 to the power negative 38 newtons, and this is the gravitational force. Now what about the ratio of Fe to Fg? So we have Fe divided by Fg will be the same as 2.3 times 10 to the power negative 2 newtons divided by 1.86 times 10 to the power negative 38 newtons. Clearly, this value of newtons will take care of this one. So we are going to have this ratio to be equals to, the ratio will be equals to 1.24 times 10 to the power 36. So we can therefore see that the ratio of Fe is to Fg is approximately equals to 1.24 times 10 to the power 36 is to 1. This tells us that what the electric force Fe is far greater than the gravitational force between two protons or between two charged particles. That said, let's move over to question 4. Now question 4a, it says state two conditions for constructive interference pattern to be observed between two sources of light. B. A parallel beam of light of wavelength 559 millimeters is incident normally on a diffraction grating having 600 lines per millimeters. Determine the maximum number of orders. Now question 4a. Question 4a. Now, which demands that we should state two conditions for constructive interference pattern to be observed between two sources of light. Now, generally, there are two principal conditions that must be met for you to have constructive interference. The very first thing is that the wave from the two sources of light must be coherent. And what do we mean by coherent? It means that the waves from each source maintain a constant phase difference. That's the first condition. Secondly, the waves from the two sources must have the same wavelength, frequency, and approximately the same amplitude. Putting that in writing, we have for constructive interference, to be observed between two sources of light, we have these two conditions. The first condition, which says the waves must be coherent. So we say the waves must be coherent. I would like to underline this word, it's very important. That is, the waves from each source maintain a constant phase difference. And secondly, the waves must have the same wavelength, frequency, and approximately the same amplitude. These two last conditions, that is the same frequency and approximately the same amplitude, are very, very important. Now let's move over to question B. Question B, which says a parallel beam of light of wavelength 559 millimeters is incident normally on a diffraction grating having 600 lines per millimeters. Determine the maximum order of diffraction, or the maximum possible order. Now, we have generally d sine theta is equals to m lambda, where d is equals to 1 over n and n is equals to number of lines per meter. M is the order of diffraction, and lambda is the wavelength of the monochromatic source of light. Now, if I make m the subject of the formula, I will have, that if I make sine theta the subject of the formula, I will have sine theta to be equals to m lambda divided by d. Now, if I try to incorporate the value of d being equals to 1 over n in this formula, I'll have this to be equals to m lambda divided by 1 over n, which finally boils down to n m lambda. Okay, now from trigonometry, we have that sine theta fluctuates between 1 and -1. That is the maximum value of sine theta is 1, while the minimum value of sine theta is -1. Now, if we try to link this up with what we have here, we will have that -1 is less than equals to n m lambda less than equals to 1. Now, for maximum order of diffraction, that is when m is equals to m max, we have that m max d will be equals to 1, since the maximum value occurs at 1. Now, for this, we are going to have m max to be equals to 1 over nd. Now, what are the parameters given to us? We are given n to be equals to 600 lines per meter, and we are given d to be equals to, that is not d, lambda. That's lambda, sorry. We are given lambda to be equals to 559 millimeters. Now, let's convert this value to lines in meters. Remember, the value of n is number of lines per meter. So, converting these values to meters, we are going to have 600 into 1 millimeter, order to the power -1, which is the same as 600 into 1 divided by 1000. To convert from millimeters to meters, we divide by 1000. So we have 1 over 1000 meter to the power -1, this -1 here. Now, this will boil down to 600 times 10 to the power -3 meters, order to the power -1, which finally reduces to 600 times 10 to the power 3 per meter. Next, we need to convert this value of lambda from millimeters to meters. So we'll just have 559 times 10 to the power negative 3 meters. Now, numerical applications. So we have the maximum order of diffraction, M max, will be equal to 1 divided by n lambda. So 1 divided by 600 times 10 to the power 3 per meter times lambda, which is 559 times 10 to the power negative 3 meters. If you quickly use a calculator, you will have that maximum order to be equals to, let me quickly punch. We have the maximum order to be equal to 2.98. Now the problem is we cannot have 2.98 orders. Generally, we have the greatest integer value of the order, and if we do this, we are going to have M max to be equal to 2. So the maximum order of diffraction is 2.
Please, if you have been enjoying the video so far and you think it's of help to you, I would like you to smash the like button, subscribe, and turn on your notification so that subsequently when we upload other videos you get informed. Equally, keep your comments coming. Drop your comments in the comment section, for that will greatly help us improve on our services.
Okay guys, let's move over to question 5. Now question 5 reads, figure 1 shows a circuit diagram containing 4 resistors and a battery of EMF epsilon equals to 4.40 volts. So we have our 4 resistors, 2 20 ohm resistors and 2 10 ohm resistors. The current I1, I2 and I3 that flows through the different resistors are well indicated. Now the question asks us to determine A, the current I1, I2 and I3, and B, the potential difference across AB. So we have our diagram. Now for us to be able to determine the value of I1, I2 and I3 and consequently the potential drop across AB, we will have to apply Kirchhoff's laws. Now Kirchhoff has 2 laws, Kirchhoff's current law and Kirchhoff's voltage law. For us to be able to apply it here, let's have a brief understanding of the laws. So we'll start with Kirchhoff's current law, abbreviated KCL. Now what does the law state? It states that at a junction, the sum of current into that junction, that is the algebraic sum of current into that junction, is 0. Normally we consider current into a junction to be positive and that out of the junction to be negative. So where to have something like this, where we have our junction here, let's say we have a certain junction here P with these branches. Now let's say we have I1 entering the junction and I2 and I3 both leaving that junction. According to Kirchhoff's law, the I1 will be considered to be positive while I2 and I3 will be considered to be negative. Now with respect to the law, we have that positive I1 plus negative I2 plus negative I3 will be equal to 0, which means that what? I1 will be equal to I2 plus I3. That is the algebraic sum of current into that junction equals to the sum of current out of that junction. The next, we have to apply consider Kirchhoff's voltage law, abbreviated KVL. Now this law, as I said, is applied across loops. And we have 2 scenarios. We have the case of a battery or a cell and the case of a resistor. Now, generally, this short bar here is considered to be lower potential denoted negative, while a longer bar is considered to be higher potential denoted positive. And current usually flows from a lower potential to a higher potential, and for that case the potential difference or the potential drop in this direction will be positive. That is a case of a battery or a cell. What about a resistor? For a resistor, current moves from a higher potential to a lower potential in this direction conventionally. What am I saying? Here we have a bulk of charges. These charges normally have taken electrical energy from the battery. So in the course of moving across a resistor RC, there is electrical transfer. That is, the electrical energy is transformed to heat by the resistor, because a resistor generally dissipates energy. So in this case, the potential difference downward in this direction will be negative. If we were to move in the reverse direction, that is positive upward, the current will be negative, and the potential difference likewise will be negative. With this, let's now see how we can apply this in our circuit. So in our circuit, the very first thing we need to do here is to indicate the junction we'll be considering and the loops we'll be considering. So we'll consider junction A and loop, and these loops moving the clockwise sense. Let's call this one loop 1, and this other loop same in the clockwise sense, loop 2. There can be a third loop if you decide to move along the perimeters of the circuit. So we'll call this one loop 3. Now we'll start by applying Kirchhoff's current law at junction A. So I'll say applying Kirchhoff's current law at junction A. Now, if you look carefully at junction A, I1 is entering the junction, meanwhile I2 and I3, they are both leaving. If that's the case, I'll have I1 will be equal to I2 plus I3. Let's call this one equation 1. What about applying Kirchhoff's voltage law across loop 1, loop 2, and loop 3? So I'll say by Kirchhoff's voltage law across, let's start with loop 1. Across loop 1. Now we are moving the clockwise sense around the loop. So moving from a lower potential to a higher potential, the potential difference in that case will be positive. So we'll have epsilon. Now if we continue in that same direction, current that flows through this 20 ohm resistor will be from a higher potential to a lower potential. Same here, I2 will flow from a higher potential to a lower potential, higher potential to a lower potential, while in the case of I3, we'll have higher potential to a lower potential. So let's focus our mind on loop 1. So we are going to have negative 20 I1. When we descend AB in the direction of current, we'll have minus 10 I3 will be equals to 0 when we finally arrive back the cell. Now, sending I2, I1 and I3 to the right, we are going to have 20 I1 plus 10 I3 to be equals to epsilon. And the value of epsilon was given to be 4.40 volt. So we have 4.4. Let's ignore the units for now. So we'll call this one our equation 2. Same, if we apply Kirchhoff's voltage law across loop 2 in the direction indicated, let's start at junction A. At junction A, we're moving in the direction of current, so the potential drop here will be negative. Likewise for the 10 ohm resistor. So we're going to have negative 20 I2 minus 10 I2. Meanwhile, from B to A, we are ascending while the current is descending. So the potential drop will be positive. So we are going to have plus 10 I3 or finally arrives point A, we are going to have equal to 0. When I simplify this, I'll have negative 30i2 plus 10i3 to be equals to 0, which finally means that i3 will be equals to 3i2, equation 3. So we have the system. I1 being equals to I2 plus I3. We have 20I1 plus 10I3 being equals to 4.4. And we have I3 to be equals to 3I2, equation 3. Now, we can solve this system with any method of our choice. You can decide to use the elimination method, you can use the substitution method, you can use the matrix method, you can use the graphical method, you can use any method of your choice. So let's use substitution. So solving 1, 2, and 3 simultaneously by substitution, we have the following. Now, let me quickly take I3 and replace it in equation 2 and 1. So I'll say from I3 equals to 3I2, equation 2 becomes 20I1 plus 10 into 3I2 to be equal to 4.4, which means that I'll have 20I1 plus 10 times 3I2 plus 30I2 to be equal to 4.4. I call this my equation alpha C. Similarly, in equation, putting I3 equals to 3I2 in equation 1, we are going to have I1 to be equals to I2 plus 3I2, which is the same as 4I2. So I call this one beta. So replacing I1 in 2, I'm going to have 20 into 4I2 plus 30I2 to be equal to 4.4, which finally reduces to 20 times 4. I'll have 80I2 plus this 30I2 to be equal to 4.4, which means that 80 plus 30 is 110I2 will be equal to 4.4. Dividing both sides by 110, I'm going to have I2 to be equal to 4.4 divided by 110. Remember, I is in amperes. Now, quickly replacing this in beta. So we are going to have beta implies I1 will be equals to 4 times I2, which is the same as 4 into 4.4 over 110 amperes. This means that I1 will be equals to 4 times 4.4, 4 times 4.4, we are going to have 17.6 over 110 amperes. Now with the value of I1 and I2, or the value of I2, we have equation 3 becomes I3 will be equals to 3 I2, which is equals to 3 times the value of I2. I2 is 4.4 divided by 110 amperes. So I3 becomes 4.4 times 3 give us 13.2 over 110 amperes. Therefore, in decimal values, we are going to have I1 to be equals to I1, we have 17.6 divided by 110, 17.6 over 110. We are going to have 0.16 amperes. I2 will be equals to, I2 is 4.4 over 110. So we have 4.4 divided by 110, which gives us 0.04 amperes, and I3 is equals to 13.2 divided by 110. So we have 13.2 over 110, which gives us 0.12 amperes. So these are the current that flows through the resistors. Now B says determine the potential difference across AB. Now if you look at AB here, according to Ohm's law, the voltage drop across a resistor V is equal to the current that flows through that resistor I times the resistance of that resistor. That means that the voltage drop across AB will be equal to the current that flows down this length AB, which is I3, times the resistance, which is 10.0 ohms. Now with I3 being 0.12 amperes, I'm going to have 0.12 amperes times 10.0 ohms, which means that VAB will be equals to 1.2 volt, and that is the voltage drop across AB.
Okay guys, if you have been enjoying the video so far and you think it's of help to you, please I would like you to smash the like button, subscribe and turn on your notification bell so that you can be informed when we upload other videos. Equally keep your comments coming. Drop your comments in the comment section, for that will greatly help us improve on our services and create better videos.